All right, we resume chapter 15 by discussing more derivatives of carboxylic acids, starting now with carboxylic acids themselves. Right? And these carboxylic acids can undergo nucleophilic acyl substitution reactions when they are in their acidic form. Right? So we have to have that H at the end of the COO group, right? This guy right here. If we are deprotonated, right, we formed a carboxylate here rather than a carboxylic acid, that thing is inherently negatively charged, so it's going to resist the approach of a nucleophile, which has their electron density. Okay. But with that in mind, right, we've got this OH leaving group, similar to the leaving group alkoxide of an ester, so we're going to have pretty similar reactivity. Yep. So much so that even though we traditionally show carboxylic acids as being less reactive than esters, they're close enough that we can actually take a carboxylic acid and convert it to an ester. And that's got a specific name that's known as the Fischer esterification. Okay, so getting a little bit ahead of the slides here, right? This is what's left for our reactivity. Carboxylic acids followed by amides. We'll talk about those soon. Carboxylates down at the bottom of reactivity. And I already mentioned this. They need to be in their acidic form so that we can actually have the nucleophile come and approach, right? Won't do that with a carboxylate. We have to be working with a carboxylic acid. And here we go. This is the Fischer esterification, right? Remember what I mentioned in class about those named reactions. They're pretty important. Fischer esterification, reaction of a carboxylic acid with an alcohol. Okay, we have an acid both to catalyze the reaction and ensure that we're keeping our carboxylic acid here in the acidic form. Okay. With that in mind, we don't even need to talk about the mechanism because, as I mentioned in a previous video, it's the exact opposite of the hydrolysis of an ester. Okay, so if you know that mechanism, you inherently know this one follows the same steps. We can also take carboxylic acids and react them with amines. And at first glance, you might predict that the reaction of a carboxylic acid and an amine would form an amide. But actually, the first thing that we get is an acid-base reaction. Okay? Our carboxylic acid group here donates a proton, right, acting as an acid, to our amine, which is acting as a base. Okay? It's got this lone pair here on nitrogen that's not shown. So the product here at room temperature is actually just an acid-base product. We get this ammonium salt over here, right? We transferred the proton from the carboxylic acid to the amine. So if we're running at room temperature, that salt is your final product. But we can heat this salt to form an amide. Okay, notice we need quite a bit of heat here. If you heat that ammonium salt, you can then form the amide. Okay, but pay attention. Okay. If it's not heated, the salt will be your final product. If it is, then you'll form the amide, okay? Just like everything else we've been doing in the past. What about amides? Okay, we're continuing to move down in terms of our reactivity. So amides are some of the least reactive of all our derivatives, okay, which is good because amides are involved in the peptide bonds in your body. Okay. So I can't take an amide and turn it into an acyl chloride. I can't take an amide and turn it into an ester. I can't take an amide and turn it into a carboxylic acid. None of those work because any of those incoming nucleophiles would be weaker bases than my leaving group in these situations. So to have a reaction of an amide, right, it is possible, but we need harsher conditions to get these things to work. Here I've got an amide as my starting material, and I not only need an acid catalyst, I need heat as well. You have to have both heat and an acid catalyst to get these to work. But if you have those conditions, then our mechanism is the exact same as the acid-catalyzed hydrolysis of an ester, right? Looks right here. We've got an amide instead of an ester, okay, but after that, all the steps are the same, right? Protonation of our carbonyl. We've got a couple of intermediates we're working between. Then we get our final product, and we want to be able to drive this reaction forward, right, with Le Chatelier's principle by using an excess of water in this situation. Okay. The good news is the final protonation here, right? Sorry, once this box disappears, that final protonation step prevents our overall reaction from being reversible. Okay. So notice that arrow down at the bottom is just a forward arrow, so we don't have to worry about going all the way back. Okay? But we do need that acid catalyst. As we've mentioned in a lot of these reactions, we need an acid catalyst to activate our carbonyl, but also to protonate our leaving group down here, right? Because we have to have the ability to make that leaving group the weaker base in the molecule. Over here, right, NH2 is not the weaker base. So hydroxide continues to stay the leaving group. We have to have the acid catalyst, right, to make our leaving group a weaker base and allow this reaction to proceed. We can also do this base catalyzed, just like the esters. We could do them acid catalyzed or base catalyzed. And what does that mechanism look like? Notice in this situation, we need 2 equivalents of hydroxide. And what's going on here? Okay, first thing, our hydroxide ion is a better nucleophile than water. So it's going to form this tetrahedral intermediate more rapidly. Okay. But if I were to just stop here, hydroxide, this OH, is still a better leaving group than my NH2 over here. So I need a second equivalent of hydroxide here to pull off this proton. Then over here, I'm given the decision, is my leaving group, right, better to be NH2 minus or O2 minus, oxide? Okay. Now NH2 minus is the better leaving group, which allows this reaction to happen. Okay, so my reaction is actually second order in hydroxide overall. One of those equivalents is consumed, so it's promoting the reaction. The other one is regenerated, so it's catalyzing the reaction. See, it's regenerated down here. Okay. From amides here, I'm going to jump straight to the nitriles. If you're following along in the textbook, notice that I am skipping the Gabriel synthesis. That's in section 15.14. I think I'm going to omit that from the material for this semester. So going into 15.15 here with nitriles, I've got something that contains a CN triple bond. Okay, so carbon-nitrogen triple bond, which is weird, right? How is this a derivative of a carboxylic acid if I don't have any oxygen in here? But I can hydrolyze a nitrile to a carboxylic acid, which is why it gets lumped in this chapter and is considered a derivative. So with a new functional group, we've got more nomenclature. Okay. How do I name a nitrile? Remember, you're only responsible for the systematic nomenclature, which is shown here on the top in blue. And they're super easy to name. You just name the parent alkane, including the carbon that's involved in the triple bond, and then put nitrile after that. Okay, so right here, 2 carbons, that's ethane, ethane, nitrile. Okay, and any substituents, of course, get named before. One thing I will note, right, is this alkyl cyanide nomenclature that's shown down here in black. It's a form of common nomenclature, and it is seen pretty often, but on a test or quiz, you're only responsible for the systematic nomenclature. So what's the hydrolysis of these nitriles look like? These things are harder to hydrolyze than amides, so you need even harsher conditions. You need an acid catalyst, strong acid catalyst, you need water, and you need heat. With all of those, you can form a carboxylic acid. The question is how? Mechanism looks like this, right here, which is pretty similar to all these other mechanisms we've seen throughout this chapter. Okay, the first step is to protonate. Now, instead of the carbonyl oxygen, we've got our nitrile nitrogen. Okay, that gets protonated. That makes my carbon right here more electrophilic and even more susceptible to this step, which is the addition of water. And then after that, I'm starting to look like some of my derivatives. Okay, so I drive this reaction forward, right? This guy here could be protonated in either position, right? I could protonate my nitrogen, or I could protonate on one of these lone pairs on my oxygen, which is what was formed right here. So why does this reaction go forward? Notice when I protonate the nitrogen to get the intermediate that's shown here on the bottom right, then I have a resonance contributor, so it's more stable. Okay. So with that extra resonance contributor, then I've formed, if you look at this, it's rotated a little bit. This is just a protonated amide. So that protonated amide is already under acidic conditions, and it will immediately hydrolyze to a carboxylic acid, which follows the steps that we just discussed for an amide hydrolysis. So why is this useful? Why are we bothering talking about nitriles in the first place? They do have a lot of synthetic applications. We saw this back in chapter 10. In nitriles, right here, can be easily prepared from alkyl halides, which is just a simple SN2 reaction. Take an alkyl halide, take cyanide, okay, put them together, then you get an alkyl cyanide here, and then you can immediately take that to a carboxylic acid in the conditions that we just talked about. So now we've got something in our synthetic toolbox to make a carboxylic acid from an alkyl halide. Just notice when we do that via this method, we get one extra carbon, right? 3 carbons over here, 2 carbons over there. We can also use a nitrile to make primary amines. This is called a catalytic hydrogenation. We talked about rainy nickel in the past for some of our hydrogenation reactions. You can take a nitrile, right, hydrogen and rainy nickel, convert it to a primary amine, and we've seen some of the synthetic applications of those as well. We'll finish this video with a discussion of acid anhydrides. Acid anhydrides are made from the loss of water from 2 carboxylic acids. Right? So I've got a carbonyl, C double bond O there, C double bond O here, and those CO single bonds, right, they share an oxygen. And that comes from anhydride, right? It sounds, you can get it right from the name, right? Anhydride without water. So it was 2 carboxylic acids, 2 COOHs, came together, lost the water. That's what we get, an acid anhydride. And this slide shows that a lot better, right? Blue right here, that's the water that was pulled out. And this is traditionally how we see the structure of an acid anhydride. You can make those by heating carboxylic acids together. And this gives us another functional group, still a derivative of carboxylic acids. How do we name them? Well, if it's a symmetrical acid anhydride, same stuff on both sides, we just name it exactly as we would either one of those carboxylic acids, because they'd be the same thing. But instead of ending it with acid, we end it with anhydride. Now, if it is mixed, right, it's not symmetrical, then we just name it as we would name the 2 individual carboxylic acids in alphabetical order, and then again put anhydride at the end. Okay? So over here, we've got ethanoic, methanoic, anhydride. Okay? Always in alphabetical order. How do these guys fall into the reactivity patterns that we've discussed in this chapter? Well, here my leaving group would be a carboxylate ion, which has a pKa of about 5. Okay. So this carboxylate then is a better leaving group than is my ester, then is my alkoxide, then is my hydroxide, then is my NH2. Better leaving group. That means that I can convert an acid anhydride into any of these. I can make an ester, I can make carboxylic acid, I can make an amide. I just can't take an acid anhydride and turn it into an acyl chloride. So any one of these reactions are valid. I can react with an alcohol to make an ester. I can react with water to make a carboxylic acid. I can react with an amine to make an amide. And just like before when we discussed acyl chlorides, I do need 2 equivalents. Okay. And this slide is again assuming that I had a symmetrical anhydride to start, which is why I'm making 2 of the same equivalents of that carboxylic acid. We'll just talk about one sample mechanism here because they all follow the same general reactivity. Okay. With my acid anhydride, I've got my nucleophile, an alcohol in this case, which adds to my carbonyl to make the tetrahedral intermediate. I deprotonate, as we've seen before. Okay. Then when my tetrahedral intermediate collapses, my better leaving group now is over here, the carboxylate, better leaving group than the alkoxide, okay, which makes my ester. And then if I'm under acidic conditions, that carboxylate will pick up another proton to make a carboxylic acid. There are a couple of considerations left in the chapter, like what if we have 2 carboxylic acids in 1 molecule, but I'm going to save that for the next video and end this one here. Okay. Any questions? Feel free to email me.